Now I said that there were 5 elements in timing machinery. I said there were 3 kinds of arrows, circles, and squares. I didn't show you a square yet, but the square was not my idea. Turns out that in 1989, by the end of the year, I had shown this idea of timing machinery to a couple of people, and one of them was Brian Stromquist, a fellow programmer at Rockefeller University who was also trained in electrical engineering. And I showed him this timing machine syntax, and he went away, and a day later came to me and said, look, we can do a phase lock loop in your notation. And I was skeptical, and he showed me something really interesting. He showed me the idea of having the timeout of a state be a variable, and he used a little square to denote that variable. Long story short, he had introduced into timing machinery an extraordinary development from my point of view that goes way beyond low-pass filters and high-pass filters and so forth. He showed me how to do one of the most interesting things in electronics, which is a feedback loop. And that's what I'm going to explain now. I want to introduce a notational convention which allows me to distribute one signal to multiple states at the same time. In other words, suppose I have an enclosure with some timing machine inside of it. To be specific, suppose there's a divide by 2 timing machine. That means that, let's say if this state is active and it gets triggered to this state by a signal Y, and so this state is now active, and another Y would trigger that second state to this third state, which then times out after an infinitesimal amount of time back to the first state. Then you could say that a Y signal arriving here will trigger from here to here and from here to here, and then a Y signal arriving while this is active would not trigger anything. However, this is active for a very small amount of time, so you would get a transition back to here. So basically what happens is you get a divide by 2 action. In other words, if a signal is emitted by the timeout of this third state up here, it will only be emitted for every 2 arrivals of a Y signal down here. Alright, so this is a simple timing machine that divides by 2. What I want to do is have it produce a result on another timing machine by incrementing a variable. Let's say x is an integer variable that starts at a value at time 0 of, let's say, 10. Okay? And so now what happens is that for, let's say, 6 y's coming in, you'll get 3 increment signals, and so x would go up to 13 for 6 y's, and so forth for any number of y's. Just divide by 2, take the floor of that, and add it to x. I'm going to use x as a variable that defines the timeout duration of this state here. So in other words, this timing machine and this timing machine are connected by these 2 signals in such a fashion that every other timeout of this state stretches the amount of time to the next state. So by itself, this system here would result in a gradual slowing down of the timeout of this state. What I'm going to do is introduce a pulse generator over here, let's say with a period of p, which decrements this variable. So by itself, if we had just this piece here, these 2 timing machines, this one would speed this guy up, because every time this times out, x would get smaller, so the timeout period of this would be smaller, and so its frequency of timing out would increase. So you have, all told, with these three timing machines operating at the same time and connected by these various signals, you have a situation where basically the decrement signals are fighting the increment signals, but twice as hard. So let's see if we can understand what the ultimate behavior of x will be. Okay, I'm going to write a differential equation to try to explain the entire scenario encapsulated in this finite diagram. Let's look at the rate at which x is increasing and decreasing. Well, it's decreasing at the rate reciprocal of p, because it's being decremented every time p times out. So far, just the left half here makes x speed up. However, every time x times out, which is every 2 times the value of x, we're going to increase x, which would slow things down. So you have a differential equation where p is a constant, it's just a given pulse rate over here, but x is the dependent variable and t is the independent variable, and so we can ask the following question, as you can ask of any differential equation: when will equilibrium be reached? Well, equilibrium will be reached when the right-hand side is equal to 0. In other words, x will not be changing if its rate of change is 0. Well, we can solve this equation for x in terms of p, right? Well, let's do it in real slow motion the way I would do it in high school. 1 over 2x equals 1 over p. Then take the reciprocals of both sides, so 2x equals p. And now you have x equals 1/2 of p. In other words, in the long run, resulting from the interaction of these decrements and these increments, x will eventually be half of p. In other words, the period of this timeout will be half the period of this timeout. In other words, the frequency of this timeout will be twice the frequency of this timeout. In other words, we have here, in these three timing machines connected by these signals, a frequency doubler.